Good evening. So today I want to go over a couple of items in a short video, hopefully short, to conclude this playlist. Normally I would go over a couple of things that I will say anyway in the classroom, so this is for the benefit of my students primarily, but even if you're not my student and you watch this playlist, you might find some of the things I'm going to say useful just to keep in mind a couple of things as you move along in your mathematical career or interest, depending on the case. So this is not an extensive review, by the way, just a couple of advice, and in particular with respect to integration, I'd like to give an overview of what we covered to make sure we understand the main idea behind the integration part of this course. A couple of remarks, and especially for those of you who are not my students, it's important to point out that this course is meant to be done in addition to the homework, because if you take every single topic that we covered here, obviously there are not enough examples in the interest of time. I mean, in some cases, maybe we'll go over 2 or 3 examples in the presentation itself. But when I teach this class, each section, every single section is accompanied by a homework. Now, if you don't take my class, obviously, you just have to pick up a calculus textbook and then go over a couple of similar examples that the one I did here in the presentation. Mostly I use problems from the well-known Stewart's Calculus Early Transcendentals book, because I find the problem set could be quite nice in that book. But the homework is essential. That's what I want to mention here. So from understanding the topics, like with any topics in mathematics, right? I mean, one needs to practice to assimilate the main theoretical idea. And getting to the material itself, I would say that the first remark I want to make is that a couple of things should be memorized, actually, even though in my class I allow students to create their own formula sheet, and they can write any formula they want, including vector algebra. If you actually expect to work with these calculus tools extensively in mathematics courses, or in other courses that use mathematics, probably vector algebra, basic vector algebra, should be memorized. So should be known well and probably memorized, because you can't really afford to actually refer back to a formula sheet or something similar whenever you need, for example, to compute a basic vector operation. So what do I mean by vector algebra here? Things like the computation of the cross product, the dot product, a magnitude of a vector, a scalar product. This should probably be done automatically. I mean, like as easy as basic algebra for calculus 1. So just like you cannot really do well in calculus 1 if you don't know basic algebra, I would say that in calculus 3 you can't really afford not to actually know very well these basic operations. And on the flip side, I mean, this is nothing extraordinary. I mean, it's just a matter of practice. You need to practice well often enough with these tools so that they become second nature. Why? Because whenever the problem has multiple steps, and in these multiple steps you need to come up with, for example, a normal, a cross product, maybe you have to compute a dot product here and there, these should come automatically and quickly, so that it doesn't act as a roadblock, so to speak. There shouldn't be, for example, any confusion, so no confusion. There shouldn't be any confusion between vector quantities, between vectors and scalars. For example, whether you take an integral of the magnitude of r prime of t, if r of t is a space curve, as opposed to the integral from a to b of just r prime of t dt, there shouldn't be any confusion at all. These two are different tools. They measure or indicate completely different entities, right? Like, for example, The first one would be the computation of the length of the arc length. The other one is a vector function, for example, finding the displacement if I give you the velocity. Okay, so different contexts. So that is with the algebra part of it. Let's talk about the integration now for a while. So as a remark, I think it's important, I think I mentioned this in passing in the last lesson, it's important to realize that there are actually, in this class at least, right? So there are basically three integrals. So there are three integrals that we learn here, that we covered. There are more than three, but what I mean is that there are actually three fundamental integrals. The other ones are essentially tools expressed in terms of these three integrals. And by the way, these three integrals are manifestations of the same. So these are actually manifestations of the same Riemann integral from calculus 1. Fundamentally, it's the same integral. The only difference is that the shape of the domain or the dimension of the domain is different. The way you compute it is different, obviously, which is the reason why we have these various, different notations like double integral, triple integral, and so on. But what do I mean by the same Riemann integral? It's the Riemann integral means it's constructed essentially following the same overall or intuitive description, right? So you start with a domain, okay, and then you're going to partition that domain in non-overlapping simple covers. The shape of the cover, again, depends on the shape of the domain. Then you're going to have a sample point from each partition element. What is a partition element? That could be a segment from the calculus 1 integral from a to b for a single variable function, could be a square or a rectangle or a cube or a box for the triple integral. So you have a sample point, then you construct the Riemann sum in the same way no matter what type of domain you have. You're gonna evaluate the function to integrate at the sample point, and then multiply by the measure, put this in quotation marks, the measure of the partition element. Now, what is the measure of the partition element? If it's a segment, that's going to be the length of that segment, hence the notation dx. If it's a double integral, if the domain is two-dimensional, so if the domain is a segment, if the domain is a region in space, the measure of the partition element is an area, hence the wording, the notation dA. And if it's solid for a triple integral, the measure of the partition element is a volume, hence the notation for dV. So I think, again, from a theoretical standpoint, it's important to point out that we really have a single type of integral that we go over in this class. The Riemann integral, not really three different ones. I mean, the difference is basically the shape of the domain. And like I said before, the convention of notation is to use one integral symbol, as many integral symbols as the dimension of the domain. So if it's a surface, it's a region in place, then you have two integral symbols. And then if the dimension is 3, then you have a triple integral. So of course it's more practical to see this as three different types of integral because they are used in different contexts, right, in lots of real-life applications, but it's really the same integral. If you go and study, for example, a more abstract real analysis, you use a single integral symbol, but then the domain can have any dimension, right? You could have, for example, a quadruple integral if you want. You're not going to write in that case for integral symbols because it's not practical, but you just indicate that the domain is n-dimensional, for example, or four-dimensional, as it is the case. So that being said, what about the other integrals? So like I said, here all the others we learned, so all other integrals are variations of these three that I mentioned, or to be more precise, or the first two that I mentioned, right? Because the triple integral, it's kind of a standalone one, but all the other line integral and surface integrals are basically manifestation of the single variable function integral, right, from calculus 1, or the double integral. Why do they actually are called different integrals? Because it's more practical to see them as different integrals, but you could basically construct the entire calculus without actually naming them as such. So what do we mean by that? For example, the line integral of a scalar field or a vector field. So this is the line integral over a scalar field, is basically set up and defined via a single variable integral when you evaluate the function at a curve. Right? So you integrate over a curve going from R of A to R of B. But as you can see, if I really want to, I could live without the notation on the left. And each time I want to compute, for example, this type of quantity that I see on the right-hand side, I could just set it out as an integral from calculus 1, f of r of t, times magnitude over r prime of t. But it's more practical to call that a new type of integral for many useful purposes in real-life applications, right? So it's more compact, obviously. But it's the line integral is essentially a version of the single variable integral. Same thing for a line integral of a vector field. And remember, we have basically two formal notations, f dot t ds or f dot dr. The first one is more suggestive because it indicates that you basically integrate over the component of the vector field along the tangent vector on the curve. And then again, this is essentially another single variable integral when you evaluate the vector field over the curve, and then dot the answer with r prime of t dt. And remember also important consequences of the, let's write them in a different color, important consequences of the line integrals. Namely that well, actually, let's actually, yeah, we'll do that on the next page. I was going to mention the conservative fields, but let's do that after we go mention also the surface integrals. So the line integrals are here, and then of course the equivalent of these for surfaces are the surface integrals. For a vector field. So let's start with a scalar field actually first. So a surface integral over a scalar field, that means little f is a scalar function, which is going to be via a double integral over the parameter domain for that surface. When you evaluate the function to integrate at the surface and then multiply by the magnitude of partial u partial v of the parameterization of that surface. Okay, so the surface is given by r of u v, which is a parametric surface. Okay, so surface integral is just a specific type of a double integral. And finally, the surface integral over vector fields. Once you choose an orientation on that surface. Another notation for it is f dot ds with a bar on the top. Another formal notation is again another type of double integral. You evaluate again the vector field, the function to integrate at the parameterization of the surface, and then dot ru cross rv or rv cross ru depending on how you choose the orientation on the surface. So there are only so there's only one integral, three types, you know, single, double, and triple, depending on the dimension of the domain, and the other ones are variations of the first two. Okay, so on the second page, I'm going to talk about a couple of things about the computation, and then the some remarks about Fubini's theorem and the actual computation of these integrals, and then probably that'll be it. Okay, so let's talk briefly about Fubini's theorem, which is the main theorem that allows us to compute a multiple integral via an iteration of simple integrals. So very briefly, I'm not going to write every single version of the Fubini's theorem one more time, but the main idea is that Fubini's theorem means multiple integral becomes an iterated integral, or an iteration of single variable integrals. There should be one variable, at least one variable with constant bounds, which should be on the outside of the integral, right? It's the last one to be computed. So basically, let's say x is between a and b, and in the case of a double integral, let's say y then can be between bounds depending on x. And if you talk about a triple integral, the third variable should be between bounds depending on the previous two. So let's say m of xy and then n of xy. And permutations of these. Okay, I mean, if you have y on the right, on the outside, you know, those will be with the constant bounds, that's going to be the outermost integral. So the integration is always from the inside out. So the integration order is from the inside out, and you always have the constant bounds on the outside. So obviously, if all bounds are constant, you can integrate in any order you want. And also remember the shortcut, you know, if you have, for example, in the case of a triple integral, if you have constant bounds all over the place, and then your function to integrate is a product of functions in x, not, let's say, m of x, n of y, p of z, dv. That's kind of a mess, sorry. This pen, I think I'm gonna not use this tablet anymore. So the shortcut when the function to integrate splits into the product of functions in x, y, and z, analogously for the double integral, you get the gist. Only in this case, again, constant bounds and this type of factorization, then the iterated integral splits into a product of functions in a product of integrals in x, y, and z. Like that. Okay, so in a nutshell, that's the gist of the Fubini's theorem. Also, don't forget the alternative coordinate systems. Very important if the domains or the function to integrate makes sense to use these alternative coordinate systems. What are these? Well, we have the polar coordinates. Right, which means x is r cosine of theta, y is r sine of theta, and don't forget x squared plus y squared is r squared, which is useful. And also don't forget that in this case, in the double integral dA becomes actually r dr d theta. Again, to make it clear, the polar coordinates are when the point is identified by the distance from the center, and the angle measured in the counterclockwise direction with the positive semi-axis, x-axis. For the triple integral, we have also spherical coordinates. Spherical coordinates. And remember, those are the distance from the point to the origin, called rho, phi, the angle measured from the positive z-axis to the OP, the point itself, right? And theta is the angle measured from the positive semi-axis to the projection of P onto the xy plane. And then the Cartesian relation with Cartesian coordinates is that x is rho sine of phi cosine of theta, y is rho sine of phi sine of theta, z is rho cosine of phi. Also, don't forget that x squared plus y squared plus z squared is rho squared, and also that the element of the volume in the triple integral dv turns into rho squared sine of phi d rho d theta d phi. Okay, so that's a brief overview of the computation in various coordinate systems. Let's talk about the major theorems, and let's put everything in the context, right? So the major theorems that we went over, the curl, the divergence theorem, the Green's theorem, these are sometimes called versions of the fundamental theorem of calculus. So let's put it together in perspective with the fundamental theorem of calculus from calculus 1, right? So they're called like that because they relate the integral of a function, the integral of a function over the contour with, or the value of the function on the contour with the integral of the derivative inside that that contour, right, inside the domain. So in other words, you have a relationship between the function on the boundary, if you want, of the domain with the integral of the derivative of that function, or a type of a derivative of that function inside that domain. So in calculus 1, of course, we know that the integral from a to b of some derivative of f, so let's say f prime of x dx, that's going to be f of b minus f of a. Okay, so the domain is a segment, so you relate basically the value of the function at the, in this case, the boundary is made of the 2 points a and b, and the inside of the domain is the segment itself. Then the line integral over a gradient field, so the line integral over the gradient field dot dr, that's going to be the function evaluated at the endpoints of that line. Right, so the c, the line is going from the position vector r of a to r of b. And remember, the important consequence here on this type of this relationship is that if you have a vector field that is the gradient of another field, then f is conservative, and the line integral does not depend on the path from the endpoints of the curve. And then we talked about how to decide that the function like this is conservative, right? So remember, f is conservative if the curl of f is equal to 0. And then into d, that means if f is, you know, the components p and q, that means dq dx is equal to dp dy. Okay, the characterization of a conservative vector field. And then remember, make sure you know that given f conservative, make sure you know to find its potential, to find f such that the gradient of f, little f, is big F, right? That's basically akin to finding an antiderivative if you want, right, in calculus 1, so that we can plug in the endpoints. Okay, so other major theorems, let's see if we can squeeze them in here. Probably we can. Let me think a little bit. Yeah, I'm trying to figure out if actually it's worthwhile to start a new page, but I don't think so. Okay, so we have the Stokes theorem, which is basically, no, I didn't mention the Green's theorem. Yeah, you know what, let's actually do another page because it's not worth it to squeeze it here. So the on the next 2 pages, we're going to mention the other major 3 theorems, Green, Stokes, and divergence, and then we'll conclude. Okay, so the major theorems, what did we talk about? Well, the Green's theorem, right? So that is in 2D. If you have a vector field with 2 components, P and Q, simply connected domain surrounded by a closed curve. And the theorem states that the line integral over this path, P dx plus Q dy, is equal to the double integral over the interior of this path of dq dx minus dp dy, which is nothing but the curl for this vector field. So that means, remember, this is only relevant if not conservative. Why? Because if it is conservative, the integral doesn't depend on the path, so the end depends on the initial and the end terminal endpoint, but if it's a closed curve, the two coincide. So if it's conservative, if conservative, remember the Green's theorem or the Stokes theorem for that matter, it states simply that 0 equals 0. So it's not important or useful. Okay, it's useful when it's not conservative, when the two quantities are not equal to 0 in general. And then you decide then which one is more practical to use, left or right, to compute the same quantity. And remember the physical interpretation of the circulation around the boundary equal to the totality of circulation inside the domain. Stokes theorem is nothing but 3-dimensional versions of the above. So 3D version of Green's. 3D version for both the curve and surface itself, right? So if you have, let's say, a closed curve like this, and then some surface enclosed by this curve, and then you orient it in such a way that if you walk on the curve, you always keep the normal to the surface to the left and up, right? Because this is 3D, right? So you have to set up an orientation on the curve. So as you walk on the curve, keep the normal oriented upward from your perspective, and to the left. Or in other words, follow the right-hand rule. So in that case, the Stokes theorem simply states that the surface integral of the curl of the vector field along this normal or across this normal is equal to the line integral over that closed curve. And then finally, the divergence theorem. Main ingredients are a closed solid, right? So imagine here you have a closed solid called denoted by E. The surface that surrounds it, let's call it S, and the normal is oriented outward. And so the theorem states that the surface integral over this of this vector field across the normal is the triple integral over that solid of the divergence of the vector field. Okay, so that was the last topic. So I think that is it, finally. I hope you enjoyed it. Have a good day.